finish off the rest of the business in that chapter on this particular application of the group SO4. And now this is a group SO4, so it consists of 6 independent parameters. The Lie group consists of 6 independent parameters, and so there are 6 Lie infinitesimal generators, so to speak. Those can be considered as basis vectors of the Lie algebra. They're the 3 components of the angular momentum, L1, L2, L3. And then the 3 sort of normalized components of the Runge-Lenz vector. And so we have L1, L2, L3. Then we define this M'1, M'2, M'3. And these 6 things satisfy a set of very interesting commutation relations which observe the general rule for SO4 Lie algebra commutations. And so let me just write these down again so that we can look at it for reference. IH bar epsilon JK LK. So this apparently forms a subalgebra because all the L's commute among themselves, so to speak. Okay. Next one we have sort of mixes the L's with the M's. So this is IH bar epsilon IJK M prime K. So when you commute the L's with the M's, you get back the M's. Okay, and then finally, interestingly, when you commute the M's, it gives you back the L's in this way. H bar epsilon IJK LK. The epsilon IJK, of course, is the completely antisymmetric Levi-Civita tensor. And so on the right-hand side of these 3 equations, for example, there's a sum over K. But if you take a particular pair of values for Ij, when I is different from J, 1, 2, for example, then the only non-zero element is 1, 2, 3. So basically, you just have one term on the right-hand side. So L1 commuted with L2 gives you IH bar L3 and so on and so forth. Okay, so the whole algebra is 6-dimensional because there are 6 basis vectors in here. When the algebra is considered as a vector space, also it's 6-dimensional, among which there's a subalgebra, which is 3-dimensional. The other one is not a sub because they got mixed like that. Okay. But there is a way to break down the 6-dimensional algebra into direct sum of 2 3-dimensional algebras. Okay, and this is the important point, simply because 6 is equal to 3 plus 3. And so we have, here write down the Lie algebra SO4. There's a way to break it down into one SO3 algebra plus another SO3 algebra. And apparently, and as we will see, each of these 2 subalgebras involve things which commute like that. Okay, this in itself is an SO3 algebra because this is just the angular momentum operator, so they correspond to Lie algebra for the rotation group, and so on and so forth for SO3. The way to break it down is this. You define out of these 6 things, you define another 6 things, which I'm going to call the 3 components of a vector that I call L plus, and then the 3 components of another vector that I call L minus. And they are very simply defined. 1/2 L plus M prime, and then this guy is 1/2 L minus M prime. Okay, so each of these is a linear combination of the L's and M's. And if you define it like this and use these original commutation relations, you're going to find that these always commute with these. The plus guys always commute with the minus guys. That means the commutator between L plus and L minuses are always 0. But the L pluses components commute among themselves exactly like an ordinary angular momentum algebra. So does the L minus. Okay? In other words, I have the commutation rules like this: L plus or minus I, L plus or minus J always produces something like this. In other words, I h bar epsilon I j k L plus or minus k, like that. You see, when you use a plus here, you use a plus all the way through. When you use a minus, you use a minus all the way through. Okay? So what that means is that each of these guys behaves like an SO3 algebra. But then you can also show that these two guys have nothing to do with each other, because L plus L minus for arbitrary components always commute, like that. Okay? And now that is very useful because of these facts. Basically, we have established this direct sum relationship. Okay? Here we have originally a 6-dimensional vector space, which is the SO4 Lie algebra, now broken down into a direct sum of 2 3-dimensional algebras, each one of which is an SO3. Yeah.
So each L is a 4x4 matrix?
No, each L is just some operator. Okay, you can represent that L by different matrices of different sizes. Depends on the particular representation. But each one of those you can just think of as a matrix. Okay, if you represent it on 4-dimensional space, it's a 4x4 matrix. If you represent it on 6-dimensional space, it's a 6x6 matrix, and so on and so forth.
So the dimension is not fixed?
Dimension is not fixed. As we see, there are many, in fact, there are infinitely many irreducible representations of the group SO3. Remember that we talk about the fact that there's a 1-dimensional representation when the total angular momentum is equal to 0, okay? And there's 2-dimensional representation when the angular momentum is equal to 1/2, and there's 3-dimensional representation when the angular momentum is 1, and so on and so forth, okay? But in general, you just think of each of these guys as operators. So they can be operators on many different kinds of vector spaces. But whatever representation you're talking about, these commutation relations are always obeyed, okay? In fact, they can operate on infinite dimensional vector spaces. In which case, you can represent them as a differential operator, like when you use to operate it on a wave function. Okay.
So say if we change the representation, would
the commutation relations would remain exactly the same.
No, the other thing, the constants.
What, these constants? These?
The structure constants would
Structure constants would be the same. Would be the same.
Even
Even
when you change
when I change the representation. Remember that Ij, Jij, Jkl, these things? And I get a string of things on the right-hand side, okay, with the structure constants that are just some delta functions and so on. Okay? These are the structure constants, right? Now these J's can be a matrix of arbitrary size. But whatever the, each different size corresponds to a different representation. But whatever the representation, the structure constants are the same. This equation is not affected regardless of the representation, because of the fact that the structure constants define the Lie algebra. There can be many different representations for Lie algebra as many as there are different representations of the Lie group. Okay? And this fact is important to keep in mind. Okay, now let's come to the important development. This is a crucial step in here, being able to break up the Lie algebra in this fashion. Now, do you recall that in the study of the quantum mechanics of angular momentum operators, you think of L as having 3 components, Lx, Ly, Lz, or I call them L1, L2, L3 in this case, out of which you can form this thing called L square, right? Which is, let me write it like this, not to be confused with the second component of L, okay? This one, according to the usual ways of defining the square of a vector, is just L1 square plus L2 square plus L3 square, okay? Now this thing formally does not reside in the Lie algebra itself, but in what's called the enveloping algebra. I won't bother you with the details, but let's just focus on some construct like this, okay? You normally think of it physically as an operator which represents the square, the absolute or the square of the absolute square of the angular momentum, or L dot L. This is basically L dot L, okay? And treated as operators, you'll see that L square always commutes with any of the components of L. Do you recall that fact? If you don't, that's fine. That's a very useful fact to know. Any operator which commutes with all the basis vectors, and in fact, and so with all the vectors inside of a Lie algebra is what's called a Casimir operator of the Lie algebra. So for the Lie algebra SO3, L squared is apparently a Casimir operator. So now, because I have two versions, two copies of the same Lie algebra SO3, I will then have a Casimir operator, which is a sum of the one corresponding to this and the other one corresponding to the second Lie algebra. Okay, so I define this this Casimir operator for the SO4, C for Casimir. Define this to be L plus dotted with L plus L minus dotted with L minus, because each one of the L plus and L minus has three components, okay? And so you can think of the dot product of each one of them with itself added together, and the whole thing then commutes with everything, right? Because these commutes with the things in here, and these commutes with the things in here, and the different L plus and L minus always commute anyway, so this is just a Casimir operator of the whole thing. Yeah?
So what's a Casimir operator?
Casimir operator is, you can, I don't want to define it fully for you. It's an operator which is an enveloping algebra of the Lie algebra, which commutes with everything inside of the Lie algebra. So you can think of building up an operator from the operators of the Lie algebra, which commutes with everything in the Lie algebra. Okay?
Like Hamiltonian?
Casimir, no, not necessarily, because a Hamiltonian operator does not, if you have a rotationally, if you have a Hamiltonian that's not rotationally symmetric, then it would not commute with the angular momentum. Okay? But for any symmetry group, for any Lie group, you can have Lie Casimir operator. Sometimes for bigger groups there's more than one Casimir operator. But it just so happens that for the SO3 there's just the one Casimir operator, which is L dot L. Okay. All right. Now the point is this, right? So by definition, the Casimir operator, so defined, commutes with everything inside of this. So it commutes with all the L pluses and all the components of the L plus and L minus. There are 6 things in here, okay? L plus 1, 2, 3 and L minus 1, 2, 3, and all of them commute with the Casimir operator as defined like this. Okay? All right. Now, the point is this, that because these two Lie algebras are the same, then the eigenvalues of each of the L's. The eigenvalues of the L plus dot L plus and the eigenvalues of the L minus dot L minus are the same. And we can actually prove that. Now, let me kind of jog your memory a bit in here. For those of you who have studied some quantum mechanics, when you consider the angular momentum L squared, do you recall what are the eigenvalues of that angular momentum operator, L squared? Let's say if you have a system, let's say the electron in the hydrogen atom, for example, and the total angular momentum is equal to L. You know, remember those quantum numbers, N, L, M, okay? L is a total orbital angular momentum quantum number. So what are the eigenvalues of L squared?
H bar squared L plus 1.
Thank you very much. Okay, H bar squared goes for the dimension, of course. In numerical values, L times L plus 1. It's not L squared, but L times L plus 1. This comes out from the representation theory of the rotation group. Okay, so the idea is that, so this has eigenvalue. Let me call it L plus times L plus 1. Eh? And this other thing has the eigenvalue L minus times L minus 1. Sorry, L minus times L minus plus 1. Okay? And so we can arrange things so that L plus is equal to L minus, obviously, because it's the same algebra. Okay? So L plus is equal to L minus. Little L plus is equal to little L minus. And according to the representation theory of SO3, I haven't shown you this explicitly. This is, in fact, one of the main stories behind, one of the main important facts behind the representation of SO3. What are the possible values of the angular momentum? They are either integers or half integers, including 0, okay? You have a completely symmetrical case, spherically symmetrical case, which is 0. So these can assume the values 0, 1/2, 1, 3/2, and so on and so forth, according to the representation theory, okay? Which I haven't demonstrated to you, but let's just take this as fact. And also you may recall learning about this in quantum mechanics, all right? The half values comes from, you know, in fact, the half values, the possibility of half values says that you can apply this to rotations of spin-and-a-half systems, such as the electrons, okay? You know that for an electron, it has spin angular momentum equal to 1/2, right? And so that the M components else is either plus 1/2 or minus 1/2, so that the spin part of the electron is described by a two-dimensional vector space, for example. Okay? All right. Now then what? Now we next show that using the definitions of L plus and L minus as given by this set of equations, you can write an alternative expression for C, the Casimir operator for SO4, which is in fact equal to 1/2 L dot L plus M prime dot M prime. This is very simple to show. Just use these definitions for L plus and L minus, stick it into here, you'll find this as a result. Okay? And so let's just keep this expression in mind. Okay. All right. Now next comes a very big step. Next comes a very big step, which I haven't proved to you in the text, nor is the proof assigned as one of the problems. But I have sent you, there are two files in the solution for this chapter that I have sent you. One file is sort of for the problems corresponding to this chapter 9. The other file is for a different set of problems which I included in my quantum mechanics text, which deals with this SO4 application also. And the proof of these is included in one of those problems in the quantum mechanics text, which I have supplied to you. So the proof of these is very important, right? Because, in fact, these shows you that the Runge-Lenz vectors and the L vectors as defined in quantum mechanics does satisfy this SO4 algebra. Okay. The other important relationship is this: that making use of the definition of the Casimir operator and that of the Runge-Lenz vector, of course, quantum mechanically we can show this. H is the Hamiltonian here, M dot L plus H bar squared plus Z squared e to the fourth. Z is the atomic number of the hydrogen-like atom, okay? E is the electronic charge, H bar, and so on and so forth, okay? Now, this is a quantum mechanical expression. Classically, H bar, of course, would not be there, okay? Classically, H bar is equal to 0. Quantum mechanical expression. The proof of this actually is quite long, but it's useful to know how that is done. So if you have time, I hope you can study the solution that I have provided to you, okay? It basically makes use of a whole bunch of commutation relations and so on and so forth between the L's and the M's as specified here, and then between the R's and some function of R and so on and so forth. It's a tedious exercise in commutation algebra, okay? One which is very useful in terms of doing quantum mechanics calculations, quantum mechanical calculations. I guess at the time when I wrote this book, I didn't think it was important enough to be included here because the purpose of this is not to do quantum mechanics. Yeah?
What did you say the Z value was?
Huh?
What did you say the Z represented?
It's the atomic number of the hydrogen-like atom, which means that you only have one electron, but in the nucleus there may be many positive charges, okay? So if it's an atomic number 6, then you may have 6 protons and 6 protons in the nucleus, and then on the outside there's only 1 electron. So basically it's still the same Coulomb problem because you're only writing a wave function for the electron, okay? So for the actual hydrogen atom, Z would be equal to 1, of course, okay? Okay, now, based on these two expressions, this one and this one, and now remembering that working within a particular representation, we can always replace H by some total energy value, okay, so that the Hamiltonian becomes a number now. I can establish this fact, that C is equal to the Casimir operator is equal to minus H bar squared divided by 2. Actually, this side now represents the eigenvalues of the Casimir operator, okay? Plus mz squared e to the fourth 4e. So the eigenvalues, we're seeing here the eigenvalues of the Casimir operator would be the eigenvalue of this guy plus the eigenvalue of this guy, okay? But the eigenvalues are the same, and each one of them is L plus times L plus plus 1. So in here, C can be replaced by 2L plus times L plus plus 1, like so. Okay? Where L plus, just like we have written here, where L plus can be any of these values. Okay, where L plus can be any of those values. Actually, there's a limit to that. Actually, you know, for a particular principal quantum number, as we'll see for the hydrogen-like problem, we'll see what kinds of values L plus can assume. But in general, each L plus, regarded as an abstract representation for the SO3 algebra, can assume any of those values. Like that. Okay. Now, if you then solve this equation for E, you see, now we are finally almost approaching the end. We can solve this equation for E, all right? And we get this simple result. That E is equal to minus mz squared e to the fourth divided by 2h bar squared 2l plus 1 squared, like that. You solve this equation for E, you come up with this result. We're up to this point. L plus can assume any of these values, 0, 1/2, 1, 3/2, 2, 5/2, and so on and so forth. So, yeah?
I'm pretty sure this because I haven't taken quantum mechanics yet.
Yes.
How are you able to replace H with E?
How do I?
So you can replace H with E.
Oh. You know that the spectrum of the hydrogen atom looks like this, right? Well, there's a bunch of degeneracies in here. This is what's called ground state, n is equal to 1, n is equal to 2, n is equal to 3, and so on. And each of these are definite energy values, okay? So I'm just saying that since H commutes with all these operators, this is the essential point, because H now has SO4 symmetry, okay? So it commutes with all the L's as well as with all the M's. Because of that, then when you can choose a subspace among the infinite dimensional space in the Hilbert space describing this, a subspace which has a particular energy value, okay? Within the subspace, the L's can still have different values to it. So I'm simply saying that I'm using these operators to act on one such subspace. It's a subspace corresponding to all the space whose vectors are all eigenvectors of the Hamiltonian having a particular energy value. Okay? This is still, it is not a one-dimensional space because there's degeneracies in here, meaning that there are many, many different quantum states which have the same energy value. I'm looking at one such subspace for a particular value of the energy. Okay? This is called also called working in a particular representation. And so if we do that, then we want to do that because we want to find what the possible values that the energy E can have, okay? So we can simply take the step of replacing the H by the E and then solve this equation for E, which gives us this result. Does that help a little bit?
So I sort of get it. Are you saying like within H is a subset E that you can use in order
H is not, H is an operator.
Yeah.
That operator acts on a certain big vector space, which may be infinite, which is infinite dimensional in general, okay? Well, that vector space can be broken down into subspaces, each one having a particular energy value, okay? In other words, let's say there's a subspace, which is finite dimensional, actually. And every vector in this subspace satisfies the condition that H acting on this vector produces the same value E multiplied by that vector. So this is a subspace corresponding to a particular energy eigenvalue of the Hamiltonian. Okay? And I'm simply working within one such subspace in here.
Okay.
And in doing so, then I can, basically, if you use this to operate on anything, since H commutes with all these guys, okay? And you can move H all the way right next to the vectors. That produces this number E times all the vectors. But if you mix up the different subspaces, then you cannot replace this by a single value E in here. Because H acting on the different subspaces will produce different values of E multiplying by a vector in that other subspace. Okay? This is more or less?
Yeah.
Okay. All right. So let's see what we can do with it. We still haven't determined exactly what that L plus is yet. But you also know that just simply looking at this equation, what is L plus plus L minus? Just L, okay? L plus plus L minus is just L. By definition. Now L in quantum mechanics, the guy which appears here represents the orbital angular momentum. So as an operator, it involves differential operators and so on and so forth acting on wave functions. And you know now that the possible eigenvalues of L, in fact, the possible eigenvalues of L dot L, okay? The possible eigenvalues of L dot L are just because L is an orbital angular momentum, possible eigenvalues of this Casimir operator must be 0, 1, oh, no. Must be L times L plus 1, where L is either 0, 1, 2, 3, like that. Okay? But on the other hand, you see from this equation, when you have, this is, you think of this just as a physics equation where there are two different kinds of angular momentum adding up to a total angular momentum. For example, one of these can represent angular momentum of one atom, and the other one of this can represent angular momentum of the other atom. And the total angular momentum of the system is just that this plus that, right? Let's say this is a total angular momentum of the system. And from the theory of the addition of angular momentum, what are the possible values of the sum of the angular momentum? Do you recall that result? This is called a triangle rule sometimes. So let me give you an example. Supposing we're looking at a 2-electron system, and we just, these 2 electrons are orbiting around some nucleus, okay? And let's say the angular momentum of this guy is 1 total orbital angular momentum, actually 1 h bar and 2 h bar, let's say, okay? As eigenvalues, okay? As eigenvalues of the angular momentum operator. Well, the question is, what are the possible values for the total angular momentum when you add these two together? Do you remember how to do that? It's a very simple procedure.
The sum of them with the difference.
How many possible values are there, first of all? There are many different possible values depending on the actual values of the angular momentum that you're adding together. If it's a case of 1 plus 2, the eigenvalue of the total, the L value for the total angular momentum can have a range of possibilities. It can go from 2 plus 1, that's the largest number, and then it can go from 2 plus this largest, which is equal to 3, and then it can go from 2 plus 1 minus 1, which is 2. And then the smallest number it can have is the absolute value of the difference of these two numbers, which is 1. So in this case, it has 3 possibilities, okay? We say that it actually goes from L1 plus L2 in steps of 1 downwards all the way to the absolute value of L1 minus L2, okay? So to give you another example. So if I want to add 7 and 8, this is L1 is 7, L2 is 8. What are the possible values of L1 plus L2? In this case, the largest one would be 15, all the way down to the absolute value of the difference between these two, which is 1. Remember that as a quantum number, all these must still be positive. So it's a range of possibilities. 15, 14, 13, 12, 11, 10, 9, 0, all the way to the 1. Okay, that's a general rule. Do you remember this? Have you seen it somewhere in quantum mechanics? Addition, this is called. All this is actually a result of the representation theory of SO3. You can look at it purely as a mathematical problem, or you can look at it in terms of the addition of angular momenta in the study of in quantum mechanics. When quantum mechanics is used to describe the angular momentum of quantum mechanical systems. Okay. Now, well, the idea is this: we have L in this case being equal to, L being equal to the sum of these two. Okay. Let's say, each of these is capable of having L plus, the same L plus, and this is L minus. L plus, a range of values possible. L minus, same range of values possible. We also know that L plus is equal to L minus. Okay. So essentially, this one is L plus also, because L plus is equal to L minus. Okay.
How do we know that?
We know that because each one of them is exactly the same algebra. So the eigenvalues must be exactly the same. Okay, and we know that C is just L plus plus L. C is just L plus 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 L minus minus, like that. Okay, it resides in the fact that it's the same Lie algebra. Therefore, the eigenvalues of the respective operators must be exactly the same. Okay. Now, if I ask you the same question again. If I want to combine these two angular momentum values, what are the possible values of L in here? It must go from 2L plus all the way to, what's the absolute value of this? 0. So it must go all the way from, the possibilities are all the way from 2L plus all the way to 0, depending on what L plus is. Okay? Now, you see the number 2L plus in here? Whatever L is, L plus can either be integer or half integer. But whatever it is, whether integer or half integer, 2L plus must be an integer, right? 2L plus is an integer, and therefore 2L plus plus 1 must be an integer also. We name that integer n, which will turn out to be the so-called principal quantum number. Okay, we define a certain integer n, which is defined to be 2L plus 1. Okay? So in this formula, I'm just going to replace 2L plus 1 by n. And now, you take a look at this. Well, n now, you see, you can already guess it corresponds to our principal quantum number in the hydrogen atom, okay? And as such, the total angular momentum can take on values so you see 2L plus, this is L, right? L is equal to whatever this is L, okay? The total angular momentum number that comes from the addition of L plus plus L minus. So L can assume a bunch of these values, right? So L can assume a bunch of these values, okay? But on the other hand, 2L plus is equal to n minus 1. In other words, L can assume values from n minus 1 all the way down to 0. You see that? L can assume all the way from n minus 1 down to 0, which means that given a particular value n, the possible values of L are 0 up to n minus 1, which is the result that you're probably familiar with. Look at the hydrogen atom. This is a formula for the energy eigenvalues of the total energy of the hydrogen atom. It's highly degenerate. In fact, it's n square fold degenerate because there are n possible values for L. So that since this is n squared, there are, the degeneracy is n squared, but that's not including spin. If you add spin, the total degeneracy is 2 times n squared, which is the rule that we know already. Okay, and so that's it. So that means that now. So how many possible quantum states correspond to this one? If you don't include spin, L can only assume the value 0 because L can only be from 0 to n minus 1. n minus 1 is 0 in this case. So the only value for L is 0 in here, right? When n is equal to 2, L can be either equal to 0 or 1. Okay? How many states are here? The Z component is just 1. These are M component 1, 0, and minus 1. Okay? So there are 4 states in here. 4 is 2 squared. Okay? And similarly, you can do it for all the rest. But when you include spin, you double it because the spin can either be plus or 1/2 or minus 1/2. So the total degeneracy for any of these states is 2n squared, including spin. Without spin, it's just n squared. It's an amazing result that you can derive the energy eigenvalues of the hydrogen atom by realizing that the Hamiltonian describing this atom has a bigger symmetry than SO3, namely the symmetry corresponding to the group SO4. Finding a particular symmetry means finding all the possible operators which commute with the Hamiltonian. It's a maximal set in this case. And we have found the 6, L1, L2, L3, M1, M2, M3. Those are the 6 independent elements of the Lie algebra. Okay? Also can be thought of as the basis vectors for the particular Lie algebra when the Lie algebra is considered as a vector space. Okay? Without the commutation multiplication rule, you can imagine the Lie algebra elements to consist of things that can be added together, such as when you add the two angular momentum. Okay? But with the multiplication rule defined by the commutation structure, you make the vector space into an algebra, okay? Because it involves this multiplication also. So this is the story, SO4. It appears to be a little bit convoluted, but originally, historically, I think Pauli was the one that figured out all the. He somehow took the clue from classical mechanics that besides angular momentum, the Runge-Lenz vector is also a conserved quantity. So being a conserved quantity, quantum mechanically it must correspond to what is called a symmetry operator in the sense that it commutes with a Hamiltonian. And then, just as in the ordinary rotational symmetry where you try to figure out all the commutation relations between the infinitesimal generators of the rotation, he tried to figure out all the commutation properties between not only the infinitesimal generators of rotation, but including all these others, and all these, then the 6 of them together form the infinitesimal generators of the group SO4. So the group SO4 is just a 4-dimensional rotation. It's kind of hard to think about physically what that 4-dimensional rotation is, but it's all in the group SO4, okay? And so he figured this out, and then without actually using explicitly, he didn't even realize, perhaps at that time, that this is the SO4 symmetry. But from these, he could directly get to here, okay? And once you have this in here, then basically you're almost home free, okay? And in the sense that you can kind of do something like that, and so on and so forth. What we have added in our discussion is to put in the realization that all this is nothing more than SO4 symmetry, okay? Pauli did that originally in 1925 by working basically all these commutation relationships of the L's and M's. And then he derived this formula for the energy eigenvalues of the hydrogen atom. Shortly after that, in 1926, Schrödinger developed his wave equation approach involving wave functions. There's no mention of wave functions here at all, okay? There's no mention of any differential operators at all here. I mean, you can use the purely algebraic properties of the group SO4 to derive that equation. But of course, Schrödinger, having developed the Schrödinger equation, Schrödinger wave function, used a completely different method to find the same thing. In other words, you know, he was able to solve for the wave function. The wave function would correspond to these three quantum numbers. The three quantum numbers, you know, correspond to the different conserved quantities in the system. That's what's called a quantum number, okay? And what happens is that he figured out a way to represent these vectors by means of a coordinate-dependent wave function. This is called a coordinate representation of the wave vectors. Abstractly, these are just vectors in Hilbert space, okay? And in fact, in quantum mechanics books, you know, x, y, z, this is the so-called coordinate representation. This is to be thought, the whole function is to be thought of as a vector. But, and this is actually infinite dimensional because these numbers can take on an infinite set of values, right? So that makes each of these kind of behave like a basis vector, right? So here it is thinking about the Hilbert space as being a function space, which is infinite dimensional because each of the basis vectors is characterized by a set of numbers and so on and so forth. But you can think of it more abstractly also without thinking about it in terms of as being actual functions of the coordinates. Actually, if you do a Fourier transform, you can think of them as functions of momenta also, okay? Or you can just think of them abstractly as vectors per se. And it's in this way that the matrix mechanics comes into play because you can now, when you think of these as abstract vectors, once you know the dimension of the vector space, then you can write a particular matrix to represent a particular operator. If you're working within a subspace that is finite dimensional, then you have a finite sized matrix to represent the operator, okay? And so on and so forth. So I think it's very important to be able to kind of move freely between the two approaches of quantum mechanics, the wave mechanics on the one side and the matrix mechanics on the other. It's just that maybe for traditional reasons, on your first exposure to quantum mechanics, you're usually, I think, more frequently exposed to the wave function approach a little bit more. But as it turns out, the wave function approach is only useful, or at least in principle useful, when you deal with a fixed finite number of particles, okay? So that you can actually write the wave function in terms of coordinates of those particles. Let's say if there's only one particle moving in three-dimensional space, I have a wave function of 3 variables, right? But as soon as you move to the helium atom, the 2 particles involving 6 coordinates, then your wave function would be a function of 6 coordinates and so on and so forth. In fact, if you have an n-electron system, then it would be a wave function of 3n coordinates. Okay? Well, what happens if I deal with electrons in a solid, in a crystal lattice? Then, in principle, it's not too practical, at least, to think of how many electrons are there in a solid. About at least 10 to the something something. Okay. Would you consider writing such a wave function? You don't see a wave function approach very often in solid-state physics. Or actually, quantum field theory, when you take into account special relativity, you have the possibility of particles disappearing and appearing and so on and so forth. Okay? In that case, definitely the number of particles in the system is not fixed. That's why you never see a wave function approach being used in quantum field theory. Okay, there are many other kinds of approaches, but never a wave function approach. In fact, even if you deal with an electromagnetic field, you don't write a quantum mechanical wave function for the electromagnetic field. You write a quantum mechanical wave function for material particles, so to speak. Okay? But you don't write a quantum mechanical. You have a classical wave function for an electric field. Those are just electric and magnetic fields. But then the problem is you have to quantize them. Okay? To quantize them, you have to somehow develop a way so you can count the number of photons, at least in principle. Or you can create photons to describe emission, or you can destroy photons when you have an absorption situation. Okay? Wave functions, remember, are only good for systems involving a fixed number of particles. The particles are always there. They don't disappear. They don't appear. When you deal with a hydrogen atom, there's always the electron. It doesn't go anywhere. Okay, it can be in many different energy states, but it doesn't get eaten up. It doesn't all of a sudden develop into 2 electrons, and so on and so forth. That's why when you deal with interaction of the problem of interactions of atoms with the radiation field, for example, which happens all the time. In fact, the very fact that we can see depends on atoms being able to emit light and so on and so forth. Okay? So in that case, there's already a fundamental problem coming out. How do you describe the electromagnetic field that is interacting with the atomic system? Okay? Now, let's say for the atomic system, you can use the ordinary Schrödinger wave function so that you have wave function describing the electron as function of x, y, z, and so on. Well, how about the photon part? Okay? It turns out, well, how many photons are there in this light coming out? Okay? So it's not very convenient, okay? So you don't use a wave function for the electromagnetic field. So there are actually, in practice, 2 approaches. One is called semi-classical, which one uses all the time in dealing with non-relativistic quantum mechanics, and that is to treat the electron as a quantum mechanical system, but the light as a classical system. It's called a semi-classical approach, okay? The other one is so-called full-blown quantum electrodynamics, where both the electrons and the photons are treated quantum mechanically. And there, you see that the wave function is totally out. We deal with operators instead. We deal with operators. Both the atomic system is completely described by operators, and the photon system is also completely described by operators. Now, this is a long road for us to try to see all the intricacies of these different approaches when one deals with even very ordinary quantum mechanical problems, but it's worthwhile to at least to begin to understand the limitations of the wave function approach. Okay. Now, why is it used so much? There must be a good reason for it. For one thing, the abstract way of dealing, the abstract, you just write down something like that in here, right? So I write down, I tell you this is for NLM, I can have 2, 1, 1, for example. So you write down using a Dirac bracket notation. This means something. This is a state vector means something, okay? But it's so abstract, you can't picture it. You can't picture it very easily, okay? But when you write this wave function as a function of x vector, then the whole thing becomes a picture, right? You remember seeing all those pictures of the different atomic orbitals presented either, in books or many places. You remember seeing things like that? So this is x, y, z. So for the L is equal to 0 wave function, is completely like a spherical blob. This means it's spherically symmetric. So one can describe the electronic distribution, which is proportional to the absolute square of the wave function by a picture like this. This basically tells you roughly where the electron is. Okay, when you go far out, it becomes thinner and thinner, so that the electron is most likely to be there. Okay, and then for L equal to 1, you have something like this. You remember seeing it's kind of like a figure 8 like this. You can picture this figure, this kind of thing as oriented in different ways to represent the different values for the orbital angular momentum. and so on and so forth. Okay, you remember seeing pictures like this? The different orbitals, the different atomic orbitals, the kinds of pictures that you see in textbooks. And this is much more appealing. I have to agree with that. This is much more appealing intuitively because you can kind of picture, oh, this is what, now the electron doesn't look like this. The electron is not a figure 8, okay? But this tells you roughly where the electron, where you can find the electron when the electron is described by a wave function that is like this, for example, okay? And when n gets to be higher and higher, it becomes very complicated. But it's all spherically symmetric and so on and so forth. Okay? So for this reason, it's much more appealing to, either when you talk about single atoms or molecules or when you talk about things colliding with each other. When you talk about things colliding with each other, you can think of these two blobs coming into contact with each other, and they kind of do its thing, and you can show a movie and can kind of show how these two things break up into different parts and so on and so forth. This is all very intuitive, all very picturesque, and so that's why it's more appealing. But the fact to remember is that in practice it's rather limited. So, and also because in chemistry one studies actual atoms and molecules, the wave function approach is much more used in physical chemistry rather than in physics. Because in chemistry, most of the time, not all, most of the time, they deal with systems having a fixed number of particles, number of electrons, and so on and so forth. So Los Alamos, for example, has developed over the decades, very, very sophisticated computer codes to calculate the wave functions of an n-electron atom. So you call them up, say, I want to find this and that wave function corresponding to the uranium atom, and then they'll crank the computers and boom, they'll generate very complicated pictures for you like that, okay? It's a very, actually even to do that problem, there's a lot of details involved, which would take 1 year to learn. That's why atomic physics is its own field, okay? But the point is that it's still limited in this regard, that it's only good for dealing with a system with a fixed number of particles, okay? Once when you go to a system with an indefinite number of particles, such as in a solid crystal, or in a case where electromagnetic interaction is involved, or in a relativistic case where particles can die and particles can be born and so on and so forth, then the wave function approach is no good. And more often you have to use the operator approach, okay? So for this reason, when I do quantum mechanics, I would like to stress the importance of not only the wave function approach, but also the operator approach also. And that is why doing the commutation relations between these different operators is a very important exercise. Okay? All right. So we have come to the end of this chapter. And it's time to take a little break before we resume the next chapter. So the test goes right up to this point. Okay? And when we come back, we're going to tell a different story in group theory, namely the Lorentz group, which is a very, very important thing in itself. So let's take a little 5-minute break. Experimentally, you know that the neutron and the proton are very different things. One is a charge, and the other one doesn't. So necessarily, they're very different things. And also the masses, even though similar, are somewhat different. And it seems that, because if the main difference is just the charge, then one can think that in terms of strong interactions, they are really the same thing. But once when you include electromagnetic interactions, they are different, okay? Because the neutron doesn't interact electromagnetically because it doesn't have a charge, for example. So we posited the theory where neutron and proton are just two different aspects of the same thing, okay? This was what led to the so-called isospin theory, two-dimensional spin theory, two-dimensional vector space, sort of as fibers existing on the base manifold, which is the space-time manifold, and so on and so forth. So that was the birth of the so-called non-abelian Yang-Mills theories. But when it first came out in 1954, it was kind of laughed out of the door because it posited that everything is massless, okay? So it cannot explain any mass, for example. But nevertheless, it existed as a very beautiful theory, and certain theorists did not give it up, okay? But finally, in the 1970s, it was realized how to break the symmetry spontaneously to generate mass and so on and so forth. And then only then did it become acceptable, as in fact, the basic theory for all kinds of fundamental interactions. Okay, so here's a case where some theorists sitting in their offices kind of dream up this theory, which is very beautiful, and so on and so forth. But for the longest time, it almost like is demonstrably wrong. It's demonstrably not the right theory, even though it's a very beautiful theory. But you can never tell. And then one day someone's going to come along that says, hey, you're missing something, and this missing part comes in, and the whole thing falls together in place again. Okay. Such the case is also with the so-called Kaluza-Klein theories, which in the 1920s already people posited there's the existence of a fifth dimension instead of four-dimensional space-time, and thus attempted to unify the electromagnetic and the and the gravitational interaction. Okay, it was a very beautiful theory, but again, you know, it soon fell into disrepute because soon afterwards it was found that hey, physics does not only consist of the electromagnetic force and the gravitational force. There are these other things called strong forces and weak forces also. Okay. So if you just unify the two of them and forget about the other two, then it cannot be a complete theory. And besides, the unification was very, very difficult. It was not understood how to bring the other two. But I guess, you know, Einstein's quest was for a unified theory. So this unification quest went for a long time and is still going on today. Okay, and so on and so forth. So you can never tell whether a certain theory is useful or not. I would, even though I don't know too much about it, I would dare say that string theory may or may not be practical, but somewhere along the way, someone is going to, yeah, sure, go ahead. Someone is going to come up with some aspects, at least, of its use, which can somehow fold it into a more complete theory or something like that. Okay? Maybe some of you will complete that job, or at least contribute to that job. I'll be dead that time.
Is that an indirect commentary on this? Is that an indirect commentary on this?
No. Look, I mean, I am, or what I am, I'm already far advanced, okay? And looking at the history of physics, and you look at the roughly time scale in which theory advances, I think it's probably unreasonable to see us being able to unify gravity and the other forces and completely explain some of the mysteries, such as the different generations of things and so on, within the next 20 years.
You never know.
And yeah, then maybe, I don't know. All I know is that I won't live for another 50 years. I don't think physics works like Moore's law because, you know, if you look at the fundamental physics that have been, I think for most of the 20th century, after relativity and quantum mechanics, those were the main giant pillars, right? After that, it was more development of maybe a big improvement in systems, okay, in ways of measuring things, in creating new instruments and studying new specific phenomena and so on and so forth. But as fundamental theories are concerned, I think quantum mechanics and relativity were really the last important ones. Because, you know, quantum field theory is a unification of special relativity and quantum mechanics, and all the rest of it, atomic physics, molecular physics, nuclear physics, and many other things, condensed matter physics are applications of quantum mechanics, sometimes with a little bit of relativity in it. And all the astrophysical phenomena that one is studying, we are still kind of living within the basic theories of relativity and quantum mechanics, okay? And one just hasn't seen any new things coming up yet, right? In terms of very basic fundamental theoretical structures. Yeah?
So do you think we might either physics, or do you think it's kind of,
Well,
of course more experiments to be run, but
yeah, there was a point in time at the beginning of the 19th century when physicists declared that all the fundamental laws are known. All that remains for us to do is to calculate the next decimal place. Those were made by very prominent physicists, I guess, like Kelvin and so on and so forth. But you know that history did not play out in that way. So it's a foolhardy business to try to predict where one is going. Okay. Well, who knows? Who knows? It's just impossible to, with new observations, us discovering new planets and being able to look farther and farther and away, and hence more and more into the past. And cosmology is becoming more and more like an exact science where one can actually measure numerical values of certain parameters and so on and so forth. You just never know, okay? But still, physics is, the unification business is not completed. We don't know what is the quote-unquote correct theory. One has trouble explaining many aspects of the so-called standard model, such as why there are just 3 generations of things and so on and so forth, okay? Or even discrepancies between the different masses within the same generations of things. Within the standard model, there are some 16, 17 fundamental parameters. Why so many? Why not just one? Or why not none at all? We would like to have none at all. Newtonian physics did not have any fundamental constants, right? When you think of it. Oh, except G. G, that's the one. But as far as other things are concerned, mass can be anything, the charge can be anything, right? But then we found that there are right now we have 3 fundamental constants, right? As we talked about last quarter, H bar and C, okay? And each one kind of designates a different area in physics. So, all right, okay, talk about relativity, okay? Talk about relativity, we talk about the so-called Lorentz group, and of course it is the group which can be considered as a 4-dimensional rotation of vectors living in space-time. Space-time comes in, at least the space-time in special relativity comes in with a special metric called the Minkowski metric. And we talk about these concepts already in our mechanics courses, and so I'll go a little bit faster. Let me recall for you that in Euclidean geometry, the metric is just the Kronecker delta function. In Minkowski physics, so in general, it's G mu nu. This is a basic construct in the so-called metric, okay, which is a second-rank tensor covariant depending on the position, a set of coordinates of a particular manifold. And the Euclidean case is of dimension 3, so each one of mu and nu can take on 3 values. In the Minkowski space, each one of mu and nu can take on 4 values, and so on and so forth. In both the Euclidean and the Minkowski space, the G mu nu is constant. It means everywhere it's the same thing. It doesn't depend on the position. But in general relativity, the thing which distinguishes it from special relativity is that the G mu nu becomes a position-dependent tensor. In other words, a tensor field instead of a fixed tensor. Okay? So let's start off with the Minkowski situation. And you recall that we usually write it as eta mu nu. It's a habit of physicists because our way of thinking that we distinguish between the 3 spatial dimensions and the time dimension, even though all of which are just different dimensions. The time dimension corresponds to the index 0, and then the spatial dimensions corresponds to the indices 1, 2, 3. And so we write the eta matrix as a 4 by 4 matrix, where the first one corresponds to time dimensional, so it's eta 0, 0, okay? Then you have eta 0, 1, and so on. And, whoop, these are lower. 0, 0, 0, 1, and so on and so forth. Now, as in the case of the Euclidean metric, the eta matrix is a diagonal matrix. And so all the off-diagonal elements are 0. And so when you calculate the length of a vector, you only have to take the terms where mu is equal to nu, okay? But this is not true in general. And in the convention used in this text, and this is based on the older convention of certain physics literature, that the value is -1 for the time dimension and 1, 1, 1 for the spatial dimension, okay? Now, there's another possibility to write this, and that is to use the value +1 and -1, -1, -1 for the spatial dimensions also. It turns out it's exactly the same thing. There's just a difference in sign, okay? It's just a difference in sign. So now, the reason why you have written like this is that you know that in the interval between two space-time points, coming back to sort of fundamental special relativity. Let's say this axis represents the 3 spatial dimensions, and this vertical axis represents the time dimension. Then, you know, if you draw a value like that, a vector like that in this 4-dimensional space, going from the origin to some point, and the coordinates at this point are t, x, y, z, let's say. 4 coordinates, right? 1 for time and 3 for the spatial coordinates. Then this metric says that you define the square of the length of the vector by what? Usually it is, the general definition is that the square of the length, okay? The square of the length of a vector is defined to be x mu, x nu, like that. Okay? Where you sum over mu and nu. There's a general way we wrote things, even in our classical mechanics course. This is the square of the length of a vector, the tip of which has the coordinates x1, x2, x3, x4, or x0, x1, x2, x3. Okay? Now in this case, when the eta matrix is diagonal, basically you just have to do eta 0, 0, x0, x0 plus eta 1, 1, x1, x1, or x, let me call this x, right? Eta 2, 2, y, y, plus eta 3, 3, z, z, okay? This is what this formula says, okay? Now, if x0 is t, and eta 0, 0 is -1, so I write this one as minus t squared, okay? And all these guys are 1, according to this convention, plus 1. And so I have x squared plus y squared plus z squared. This is the square of the length of this vector, okay? Now, you know in physics terms, x has a length dimension and t is a time dimension, so it's like adding apples and oranges. It's not quite right, okay? And so you make the dimensions right by doing what? By multiplying c squared, by multiplying by some velocity, okay? C in this theory of relativity is interpreted as the speed of light, which is a fundamental constant of nature, okay? So its value doesn't change wherever you go and whenever you go, okay? And this is in fact the way you see the length of a vector, the square of the length of a vector written in old physics text, okay? So x squared plus y squared plus z squared minus c squared t squared. Now, in doing field theory or more general work in relativity, since c is a fundamental constant, you have the option of choosing a system of units where c is equal to 1. That's what we did in classical mechanics way back. And this is a way that this is called a natural system of units, where c is equal to 1, and h bar is equal to 1 also. Because in quantum field theory, you work in both the special relativity and the Planck's constant at the same time. Since both are fundamental constants of nature, you just choose a system of units, since they appear all the time in physics equations, right? H bar and c. They're constants. So why don't we choose a system of units where each of them is equal to 1? So we don't see them anymore. And then, you know, there's only one fundamental dimension, right? And so on and so forth. So for this way, in this way, we choose c is equal to 1, then we have these values for eta, minus 1 plus 1 plus 1. Or if you choose this, then it just becomes plus t squared minus x squared minus y squared minus z squared. It's okay too, all right? It's up to a sign, so to speak. Now, if you look at the so-called light cone, so let's think of things physically. Light cone, where this line is 45 degrees, okay? So on this light cone, how is this light cone defined? This light cone is defined when the length of the vector is equal to 0, okay? So x squared plus y squared plus z squared is equal to t squared, okay? So that means an event on the light cone, okay, satisfies this condition in here. Now, you know that special theory of relativity posits that things with mass can only travel with a speed that is less than the speed of light, okay? So if things can, you put back the light in here, okay? If things can travel only with speeds less than light, then which term is bigger? And this term must be bigger than the sum of these three, okay? You think of a thing going from here to some point, okay? So now, for vectors in here, we call these time-like vectors, okay? What are vectors in here called? Light-like or null-like, because the length of the vector is equal to 0, which is very funny. A non-zero vector having 0 length. This is a strange thing about the geometry of relativity. A non-zero vector having 0 length, which you never see in Euclidean geometry, okay? And also you see something also funny, and that is, for here, apparently, for light-like for example, okay, which are vectors in here. These are called null-like. For light-like vectors, c squared t squared is bigger. So the whole thing is bigger than x squared plus y squared plus z squared. So the whole thing is negative. For space-like vectors, which are vectors outside of here, the other situation is true, where x squared plus y squared plus z squared is bigger than c squared t squared, okay? So you take the square of the length to be positive in one region and 0 on the cone itself, then the square of the length must be negative in the other region, okay? So because of this non-definiteness, that the square of the length of a vector can either be positive or negative, it's called non-definite geometry, okay? Or non-positive definite, yeah?
Just a random thought.
Yeah.
So I understand that on the one line.
On the cone, on the light cone.
45 degrees space is light-like, and nothing is matter can go faster than that.
Yeah.
Nothing goes faster than that.
There's no communication between the two regions, in the sense that you can send a light signal from one region to the other. Okay.
But does that incorporate the idea that space itself travels faster than light?
Space itself travels fast. What do you mean by that? What do you mean by space travel? You mean inflation of space?
Sort of.
That can happen. The inflation theory does posit that. Okay, that's one theory in cosmology. Okay, that somewhere in the past, way past, not long after the Big Bang, then there's sudden inflation, so that the effective distances expand at a very large rate, maybe perhaps bigger than the speed of light. Okay, so the space itself is actually space-time actually itself is expanding, or in some scenarios, only space itself is expanding. It's like if you look at a balloon. This is very often the paradigm used to explain this. If you take a balloon and draw dots on the balloon, and take the balloon as space itself to two-dimensional space, and the balloon expands, and suddenly the dots are getting farther and farther away from each other. That's the expansion of the universe. A very crude kind of analogy, okay, and so on and so forth, okay. If you look at these two-dimensional surface, there's no point which can be regarded as the center of the universe, okay. Each point is just like any other point. But yet, you're going to have a scenario where as time goes on, the dots go farther away from each other, okay? So if originally you're very close to each other, like your next door neighbors, in time, whoop, you're very far apart, okay? And so on and so forth, okay? Well, expansion, maybe, is this what you mean by expansion of space? Space itself traveling faster than light? It's possible. Space itself can travel faster than light, but material particles with non-zero mass cannot travel faster than light. On the other hand, particles with zero mass has to travel at the speed of light. This is basically the theory of relativity, and we can work all this out based on the representation theory of the Lorentz group itself, which gives us the different kinds of particles that are possible, particles of different spin, and so masses, and so on and so forth, okay? And then it tells us what can travel with what speeds and so on and so forth, okay? So a lot of the physics that follows from special relativity is in fact a consequence of the mathematical theory of the representations of the Lorentz group, because there are many, many different representations, okay? All right, let's go back to study the Lorentz group itself. It's a group, first of all, okay? And what is this group? This group is defined in terms of a property that resembles the ordinary three-dimensional rotation group that we have seen. How do you define the ordinary three-rotation group? Working on three-dimensional vectors, you define it as a set of transformations which preserve the length of the vector, all right? Certainly when you rotate vectors, you don't change its length. But there's more than rotations if you just include the preservation of length element in it. An inversion, which is not a rotation, preserves the length also, okay? An inversion, definitely. So the group O3 includes all the rotations and all the inversions or inversions times rotations and so on and so forth, which can have the determinant of the transformations either equal to +1 or -1. And that is a mathematical consequence that we have worked out explicitly last quarter, that if you require just the preservation of length, the determinant can be either equal to +1 or -1, right? Very simple. Why? O3, orthogonal, okay? An orthogonal matrix means that the matrix times its transpose must be equal to the identity matrix, okay? So then you work out the determinant, both sides. The determinant of a product is equal to the product of determinants, so your determinant R times determinant R transpose must be equal to the determinant of the identity matrix, but the determinant of identity matrix must be equal to 1. Just multiply a string of 1s together, okay? The number 1. But you also know that the determinant of transpose is equal to the determinant of the matrix itself, okay? So this says determinant R squared must be equal to +1, okay? So basically implies that the determinant of R must be either equal to +1 or -1, okay? And this goes for the O group. But if you add the requirement that the determinant has to be equal to +1, then you get a subgroup out of there, which is then the group SO3, which represents all the actual rotations, okay? So in a similar sense, you can kind of generalize this idea to the set of transformations on four-dimensional space-time which preserve the length of four-dimensional vectors as described, as dictated by the metric that we have just given. So the set of Lorentz transformations is then defined to be the group of transformations can actually easily show that satisfies the group properties. So the Lorentz group is then the group of transformations on four-dimensional vectors which preserves the length of four-dimensional vectors according to the Minkowski metric. Okay, that's the definition of the Lorentz group. Now let's write this out more carefully. And so let me introduce this notation. Supposing I have a vector x. I'll write something x without an arrow sign because the arrow is very often used just for three-dimensional vectors. So I'm going to take the liberty to write this as a vector. And I'm going to use this notation to mean the absolute value of the length of the vector, okay? Or just the length of a vector. And the length of a vector, now the length of a vector squared is then defined in this way, right? X mu, as we have just written down. This is defined as the square of the length of the vector. And using the metric that we have just introduced, minus 1, 1, 1, 1, the rest are zeros. This is just equal to x0 minus x0 squared. Now instead of x, y, z, I'm going to use x1, x2, x3. So plus x1 squared plus x2 squared plus x3 squared. Okay? Now, a rotation on some vector in Minkowski space whose components are x0, x1, x2, x3 has to be a 4x4 matrix, right? So let's say I apply some 4x4 matrix which I call big lambda, so it has components lambda 0, 0, lambda 0, 1, and so on and so forth, okay? And you multiply 4x4 by a 4x1, you end up with another vector, okay? Which we call x prime 0, x prime 1, x prime 2, and x prime 3. And so let me just write it like this. This symbol just means this multiplication in here, okay? 4x4 matrix multiplied by this column matrix in here, which is itself a vector in here, okay? And supposing I want to calculate the square of the length of this vector, okay, using the same metric. The metric is constant, okay? That means minus x prime 0 squared plus x prime 1 squared plus x prime 2 squared plus x prime 3 squared, which is the square of the length of the new vector. And the definition of a Lorentz transformation is a lambda such that when lambda acting on x produces a new vector whose square of length is remains invariant, same as the original square length, like that. This defines the, as we'll see, this defines a set of all Lorentz transformations for you. For every vector x in Minkowski space, which in this chapter I'm simply going to call M. So M is our four-dimensional Minkowski space, our four-dimensional space endowed with this particular Minkowski metric, so it's called a Minkowski space, okay? It's a metric space, where in which you know how to calculate lengths of vectors and so on and so forth, okay? If a transformation satisfies this property, much like the rotation matrix operating on a vector x does not change its length, then this matrix is called a Lorentz transformation. And you can show that the set of all Lorentz transformations form a group. All right? How do you show that? You show that if lambda 1 and lambda 2 are different Lorentz transformations, and lambda 1, lambda 2 is also a Lorentz transformation, which is pretty obvious, okay? Just as any rotation is an inverse, any Lorentz transformation is an inverse also. You can undo the Lorentz transformation, okay? And obviously there's the identity, okay, which is just the identity 4x4 matrix, okay? And obviously the multiplication matrices satisfies the associative rule, which is required for any multiplication in the definition of groups. Then the set of Lorentz transformations defined in this way clearly forms a group. It's called a Lorentz group. Okay, let's try to then find out some consequences of this particular requirement in here. The consequences of this requirement for three-dimensional vectors having a Euclidean metric comes out with the orthogonality rule that R times R transpose must be equal to the identity. This comes out with a different rule, different rules, as a matter of fact, okay? Let's try to find out what those rules are. Now, first of all, I'm going to write this in terms of components, this transformation in terms of components, which is something we've done all the time. So, in fact, x prime mu I'm going to write this as lambda mu nu x nu, where the nu is summed over. And again, I'm going to use a convention where the bottom index is a row index and the top index is the column index of the matrix. So my lambda actually is like lambda 0, 0, lambda 0, 1, lambda 0, 2, lambda 0, 3, lambda 1, 0, lambda 1, 1, lambda 1, 2, lambda 1, 3, lambda 2, 0, lambda 2, 1, lambda 2, 2, whoops, 2, 2, lambda 2, 3, lambda 3, 0, lambda 3, 1, lambda 3, 2, lambda 3, 3. Okay. And so if you have to write this out in terms of matrices, actually this is not quite right. I wrote it wrong. You find that if I have to write it like this, where the upper and so on, this is not a matrix. It has to go like this. It has to go like x prime 0. These components has to appear as row vectors now. X prime 1, x prime 2, x prime 3 is equal to x0, x1, x2, x3, and then the lambda matrix that I have just written down. Lambda 0, 0, lambda 0, 1, lambda 0, 2, lambda 0, 3, and so on. Lambda 1, 0, lambda 1, 1, lambda 1, 2, lambda 1, 3, and so on and so forth. See, okay, okay, and you see that this equation, this matrix multiplication equation, is actually this one in here. Verify that. Okay. So x prime 0, for example, is x0 times lambda 0, 0, x1 times lambda 1, 0, x2 times lambda 2, 0, x3 times lambda 3, 0, and so on. So, and similarly for the other things. Okay. The rule is that, you know, this mu is a free index in here. So the mu, which appears as a superscript on the left-hand side, must appear as a superscript on the right-hand side also. Otherwise, you will not have a correct tensor equation. Okay. And then since we agree to write the matrix multiplication, write the matrix in this way, where the bottom index is a row index, then the equation appears to be like this, where the mu is summed over in here. Okay. Now, such a set of lambda matrices satisfying this property is called a Lorentz group. It is simply many times just designated L4. The 4 means it's acting on 4-dimensional vectors. L means Lorentz. Okay. Sometimes, because of this kind of sort of something that generalizes the orthogonality concept in terms of 3-dimensional vectors, you also write it as, you don't write it as O4 because this would then mean what? This would then mean the set of orthogonal 4x4 real matrices, okay? But it's not actually orthogonal, as we'll see. How we distinguish this sometimes is to write O13, which means that among the 4 components, there's one, when you figure out the length, has a different sign attached to it. There's just this one dimension that has a minus sign attached to it. The other 3 has the opposite sign attached to it. Okay? So you distinguish that in that way also. But most of the time, let's just write this as L4. Let's just write this as L4. Okay? So this is a requirement for constant length. So in a sense, it is a rotation in 4-dimensional space, which has a really funny geometry that is specified by this metric in here, okay, which is very different from an ordinary rotations in 3-dimensional space having a Euclidean metric. This is rotations in 4-dimensional space having a Minkowski metric, okay? Now, when you think in physics terms, though, even in 3 dimensions, you think of the possible motions of a frame, right? Aside besides rotation, there's a translation also. We think of parallel displacements of frames, and then you can have all. So how do we make a bigger group out of the rotation group? In other words, incorporating the translations with the rotations, okay? Now, to do this properly requires a new mathematical concept, which is called a semi-direct product of two groups. We think of this group, this group, which is composed of product of two groups, one of which is the translation, and the other one is the rotation, which is the Lorentz transformations. And this group involves transformations like this: x prime mu, aside from being equal to this, which is just a rotation, has to involve a translation also, which means we put a constant translational vector whose components are a mu. Okay, now these things also form a group, as you can show. It's a bigger group than the Lorentz. It's a bigger group than the Lorentz. Okay, it's a bigger group than the Lorentz, and in fact, there's a name attached to this group. It's called a Poincare group. It's called a Poincare group, which involves all the four-dimensional rotations as well as the translations. Okay. Now, the translations. The translations can be thought of as this, where this is the identity in here. Okay. So if this is the identity, x prime mu would be just x mu plus a mu. That's a simple translation part. So the translation is obviously a subgroup of the whole Poincare group. Okay? The translational part we write T4, T4 translation. Translation in 4 dimensions we write T4. And as such, you can show, I'm not going to do that explicitly, obviously it's a subgroup of the whole Poincare group. Okay? It's a subgroup involving always the identity right here. Okay, and then whatever these are, okay? It's a subgroup, okay? And you can also show that it's a normal subgroup in the sense that we have discussed it in the last chapter, okay? And obviously, the translation group is an abelian group. You can translate one way first and then the other way. It doesn't matter which way you go first. So it's an abelian subgroup of the Poincare group. So T4 is an abelian subgroup of the Poincare group, which is at the same time so it's a normal abelian subgroup of the Poincare group. It's a normal abelian subgroup of the Poincare group. Now, and we can write it like this. Then the Poincare group is what is called the semi-direct product, S for semi in here, times T4. So that anything in the Poincare group, G, can be, so G is something in the Poincare group, can always be written as a product of, some lambda in the Lorentz group times some translation, okay? And these are to be thought of as acting successively on a particular 4 vector, okay? So in this sense, so these are 2 different groups, okay? But when you form it together in this way, the whole thing where, you know, a particular element, this whole thing is defined to be these 2 things operating in succession, forms a bigger group that is called a translation. Called a Poincare group. So the Poincare group is a semi-direct product of the Lorentz group with Steve.
I think we're off now.
Oh, I'm sorry. Okay. And this is a good point to stop. Semi-direct product.